All right, so let me say a word about the next homework here. Okay. So, oh, by the way, note that the due date is 2 weeks from today. This isn't due till the 17th. So the first one is, suppose that you have a divisible abelian group as per last time. Show that any homomorphic image of a divisible group is again divisible. So these are preserved under homomorphic images or quotients, however you want to think about it. Show that if G is any abelian group, then G may be decomposed into a direct sum of D direct sum N, where D is divisible and N has no non-trivial divisible subgroups. Let me point out the identity group is always divisible, and that's what I mean by a trivial one. Notice, of course, if G itself is divisible, then N would be 0, for example. And C, show that any abelian group, so this is along the lines of what I was saying to you all earlier, show that any abelian group can be embedded in a divisible abelian group. So given any abelian group A, there is a one-to-one homomorphism from A into some divisible abelian group, right? This is sort of the prelude to any module can be injected into or can be embedded into an injective module. Number 2 is 10 points because it's an if and only if. Show that if you have a sequence of R module homomorphisms, and that's not a typo, there is no 0 on the end. So F is 1-to-1 and the image of F is equal to the kernel of G, but G doesn't necessarily have to be onto. Show that this is exact if and only if this sequence is exact. And we're going to talk about what this means, but these are new R modules. This is the homomorphisms from D to A, the homomorphisms from D to B, and the homomorphisms from D to C. So if this is exact, this is also exact for any R module D. And if this is exact for every single R module D, then the original sequence. And number 3, we're looking at some interactions between homomorphisms, direct products, and direct sum. Recall what this is, of course, these are the R module homomorphisms from the direct sum of AI into B. Show that the homomorphisms from the direct sum of AI into B is isomorphic to the direct product of the separate homomorphisms from AI to B. Right. And then give me an example to show that in general, the homomorphisms from the direct product of AI to B is not isomorphic to the direct product of this. So see if you can give me a concrete example to show that this isomorphism, there is no isomorphism in general like this. And finally, this is sort of to come full circle on this. Suppose you have R, it's a commutative ring with identity. Show that every R module is free, if and only if R is a field. By the way, one direction, if R is a field, then certainly every module is free because it's all vector space, right? But the interesting part is the other way. It's not super hard. Let me give you a hint. What distinguishes a ring, or what distinguishes a field from just ordinary rings? Well, there's that, but see if you can think of that in a more ideal way. Okay. Any questions? All right. Okay, so let's kind of pick up where we were last time. Oh, yes. I wanted to complete this theorem. I think it was 666 on projectivity. Right. So let me just kind of quickly remind you all of the contents of what we're doing. And you all have the dual theorem actually for injective modules that you're doing on your homework, but we have the following. So one is injective. And recall what that means. If you have A, B, C, or to see what that is, exact. So that means that this is on to. And you have P, G, then there exists an H such that when you do H and then you exact G. Right? And I think I may have used the letters in different order, but it should all be the same. Two, every short exact sequence of form 0, A, B, P, 0 splits. And three, there exists free F such that F is isomorphic to P direct sum A. So these were the conditions that we had. These are all equivalent, any module. So these are the equivalent conditions for being projected. This one's one of my favorites. Last time we had 1 implies 2, and 2 implies 3. And so we'll finish up today. We'll do the last implication, 3 implies 1. So we know that F is, or I'm sorry, that P is the direct summit of a free. We need to show that it is projective. So I'll use 1, 2, and G, P. We need to show there exists H and P to A such that when you do H and F, you get G. So really what we got to do is we've got to find this H. And we also, the tool that we have is that we know that P is the direct summit of 3. So let me kind of draw this diagram again. Now, we got to get from here to here, right? And the only thing that I can really use that I've got at my disposal here is the fact that P is the direct summit of some 3. So we know that there is a free module, P sum K, right? And I also know something else. Lucky for me, I can get from P to P sum K here by inclusion P, and I can get back down here by projection on P, just to make clear. And P, everybody good with that? Now, what do I want to do here is I need to get from P to A. Don't really know I can do that yet, but I do know I can get from here to A. I do know there exists an H prime here such that from P sum K into A such that when I do H prime, then I do F. This is the same thing as going all the way down. I P first, and then G. How do I know that? So notice that pi PG goes from here to here. I've got F going from here to here. So I have to have an H prime such that going H prime F goes all the way down to pi PG. And the reason is this is free and hence projective. So A, free, hence. That was the theorem. Quite cool. Now, how are we going to define H? What is the sagacious way, perhaps, to define H? Right. All I need, let me just find what would seem to be the most logical path from P here. I can't go this way because I can't reverse myself. But if I go up here and flash down here, that seems reasonable. So we will define H to be an inclusion into P H prime, and this goes from P to A. Now, to complete my thought here, what I need to do is verify that we need to show that when I do H, then I do F, I get G. Okay. So let's finish it off. Let's do H, F. Well, H is H prime over P, right? But if I look over here, this is G pi P. So I can replace this by G pi P over P. Right. But notice that I over P pi P P equals pi P of P comma 0 is P. So this thing is actually the identity on P. So that's and they also. So the modules. Everybody okay with that? All right. Okay, and when you do your homework, you probably noticed that there was some mirror image stuff going on there, which is good because these notions are dual here. So let me give you a corollary here. And this is one of the reasons why the characterization of projective that is it's the summon of a free module, I think is really kind of one of the slickest things here. So let's look at the following corollary. 6, 6, 8. Let PI be a family of R modules. Then the direct sum is projected if and only if PI is projected for all I. Okay, how are we going to prove this? which one is easier? They're both essentially the same. Let's go this way first. Let's suppose the direct sum I PI is big. And let J be any index in here. Okay. Notice for some R mod K, the direct sum PI, direct sum K is free. Great, because that was one of our equivalent characterizations. So let's rewrite this a little bit. This is, I think I can leave this over here. This is isomorphic to PJ, direct sum PI, I is not equal to J, direct sum K is free. And so PJ, direct sum big mass is free. So PJ is projective. Right, okay. That almost feels a little dirty, right? Like I'm cheating or something. How about the other way? So what we've shown is if a big collection of modules, if their direct sum is projective, then every piece had to be projective. Now what I want to do is show if everything is projective, if all the PIs are projective, then their direct sum is also projective. Let me give you a little fact that will be useful here. Note first that we have Fi are all free, then say I is some other index set, J that is because every one of these separately is a direct sum of some number of copies of R. So let's say, I'm probably going to regret doing this. Let's say that Fi is the direct sum of R. Let's say I. Let's say or some index set. Right. So Fi is a sum J in lambda. There we go. So each Fi is a direct sum of some number of copies of R. So this thing right here is the direct sum I and J, direct sum J in each lambda I R. And so an even bigger collection of direct sum stuff in R of copies of R, so it's free. So we make that observation that the direct sum of frees is free, and that pretty much does it for you. Because since each PI, I in my original index set I is projected, there exists KI such that PI direct sum KI is free. Right. Therefore, the direct sum is free. 5 preceding months. No, quite sure how to use that word. How about previous remark? So the direct sum of PI and so Bill direct sum Fred is free. So this is projected. One thing, of course, that I did leave out is the fact that this thing is isomorphic to this. I'll leave that as an exercise to show. It's not too difficult to show that these two objects are isomorphic. Okay. Okay, so what we have, corollary 668 is projected. If you have a collection of R modules, then the direct sum of that collection is projected if and only if each bit is. What do you think it is for injectives? Any idea? It's almost
bigger direct, but not direct.
Oh, I think you're right.
Yeah, but I lost the word. Direct product.
But I see J is some index there. The family of R modules. Then the direct product IJ is injected. If and only if IJ is injected. Probably. And I'm going to leave that one as an exercise. There's some similarities there, but you might kind of go through that and see if you can figure out the subtle differences. And let me give you, I want to give you one final theorem before I start talking about Hom. And I'm going to leave this as a kind of an exercise to think about part of it, but I'm going to kick you down the road a little bit to sort of start off the proof, to give you an idea of where to look. This is something that we use in the homework. What do I call that? Oh, I did skip something. I'm sorry about that. And this should be 669. So I'm actually going to do two more things. Corollary 6610. Let me this one, when you see what I write here, will require no proof because you've actually got a stronger result. However, if you're interested in things like homological algebra, sometimes people are very interested in things like projective and injective resolutions. And even though this is true in a much more specific case, I'm going to record this here. Corollary. Every R module is the homomorphic image of a projective R module. Somebody tell me very quickly why that has to be true given what we know so far.
It's a homomorphic image of a free module and frees are projected.
That's exactly right. That's the shortest shortcut to that is every R module is a homomorphic image of a free and all frees are projected. actually, let me give you an example that I'm going to come back to much later in the course, actually, when we're doing stuff on different domains. Let me give you a quick example, just to kind of, for fun, to think of, that I might come back to. How many of you have ever encountered this ring in your travels? Right. This is, of course, a set of complex numbers, a plus b radical -5, a, b, and c. Is anybody like in the beginning algebra class or number theory class, something like that, ever seen this animal? This is like sort of one of the first sort of examples that you get about factorization being bad, right? Notice that in this ring you have 6. And notice that 6 is 2 times 3. And it is also 1 plus square root -5, 1 minus square root -5. How many of you have ever seen this example and you go through and you prove all these things are irreducible, and so this thing doesn't have unique factorization? Have you ever encountered this? This is actually ring is actually, I can use this a little bit as a source in the integral domain setting, as opposed to the example I gave you last time of an example of a projective module that is not free. But I be the ideal generated by 2 and 1 plus radical -5 in this ring. So it's every linear combination 2R1, this thing times R2, where R1 and R2 are here. This is an ideal, this is proper. As an R module, I projective, but not free. And when we get to invertible ideals, I will give you I'll give a more thorough treatment of that, but you might kind of play around and see if you can show that. Finally, six, 11. Every R module M, we'll say R is commuted with identity, can be embedded and injected. So I'll leave this mostly as an exercise for you to think about. Embedded, of course, what that means is if I walk up to you on the street, give you an R module M, there's a 1-to-1 homomorphism from M into some injective R module. And when the outline beginning of the proof, as an abelian group, M can be embedded in a divisible abelian group. And that's a homework exercise that I just introduced, actually. Now embed M. This time it's an R module in the injective R module home Z of RD. So put M inside the divisible building group D, then consider home ZRD. Homomorphisms from whatever R is into this divisible building group. Now consider that as an R module and see if you can finish this off. Okay. Any questions? Okay, so now let's introduce home. This is gonna, I always have to write this down, think about this a little bit, right? Because when I do algebra, not analysis, I always have to think about function composition. So recall, how many of you have ever heard of tensor product? Right? Have you, has anybody ever encountered tensor product in like a linear algebra course? I don't know, I don't know if they do that. Physicists seem to attempt to use them with impunity, although they're just pushing symbols around. Actually, home, as you might guess, means homomorphisms, right? And we've seen this notation before. This is actually intimately related to the tensor product, believe it or not, and we're going to tie this together later. Well, let's recall first that if I say home R A B, this is the collection of F from A to B, where F is an R module, homomorphism. And so I'm going to assume everything's nice here, R is commuted version of identity, and we already know that home RAB itself is an R module under pointwise addition of functions and multiplication, scalar multiplication, R times F is the RF of A is R times F of A. There we go. Right. So we are going to consider R module homomorphisms. Right. So let me show you how you might play around with this. So consider R module homomorphisms. Let's say gamma from C to A and little tornado guy from B to D. Gamma C to A. Then you can use this. Please allow a map from home RAB, home RCD. And how are we going to do it? How are we going to get from home RAB to home RCD? Well, let's let us let F be a homomorphism from AB. And somehow I want to use these given tools to get a homomorphism from C to D, right? So here's what we got. From A to B, we have F. Right? Now, how can I use that to get a homomorphism from C to D? Well, I need to, my domain for the new homomorphism has to be C. So I started A here, so let's do this. That starts at C. And how do you suppose I get to D? Same trick, right? So F gamma. So I'm using function composition. I'll start here to get here. And so forth. Now, we're gonna really specialize this. The assignment here is actually an R module homomorphism. It's fairly easy to check that this works well under sum and under the multiplication, since these are both R module homomorphisms as well. We're not usually going to use such generality. We'll specialize to a couple of cases here. What do you say? This is homomorphism induced by gamma and the other guy. Now, here are some special cases that we're going to focus on. Number one, you might have B and D. If B equals D, and of course, the easiest thing I can think of is if this little tornado guy is actually the identity on D. Then F goes to oh, says if you oh, C to A, right? So this map is F goes to F gamma. And sometimes this is induced by gamma. So we say that this induced function, your input is F and your output is F gamma. On the other hand, we can specialize at the other end of this little diagram here. If A equals C, and gamma is the identity on A, then the map is F goes to right. And this is sometimes called map induced by. So in this case, that. Okay. So these are called, so remember in this kind of setup here, the gamma and the tornado guy, these are fixed homomorphisms. They're fixed, they're stuck in time. Whereas the F, that's sort of the variable, right? So for different values of F, this gives out different outputs here. So let's go ahead and get busy with the first theorem. Some of this you've seen in the homework. So this one's theorem 7.1. Let R be a ring let me break this up. One. The sequence of R modules 0 to A, B, C. FG is exact if and only if the sequence 0 into home R D A into home R D B into home R D C is exact for all R modules D. Right, so, and again, this is not a misprint. What this means here is that the function f is 1-to-1, and it means the image of f is equal to the kernel G, but G may or may not be on it. We don't know that G is on it. And we get the same sort of treatment down here. This is the map induced by f. This is the map induced by G. Okay, and when I do the proof, I'll kind of tear this apart a little bit more. This exact means this is exact for all R modules D. This exact for all R modules D means this is exact. Everybody okay so far? By the way, there's something going to be different for the other one. Additionally, too, notice that this is off the other side, right? Now, f may not be 1-to-1, but the image of f equals kernel G, and this time G is the one that's, I know it's good to go, it's on to. This is exact. If and only if. Anybody want to guess what happens here? Nice. Home R CD. Home R DD. Home R A. This actually shows, you might have seen hints of this before, but there's kind of a duality notion between 1-to-1 and onto. They're intimately related. And see, this is what's weird, right? First of all, the stupid functions seem to be going backwards, don't they? Right? We're going, F goes from A to B, and now its analog goes from B to A, sort of. Right? And what else is too weird for color TV is it apparently turns this thing, which is onto, into this thing, which is supposed to be 1-to-1. Right? Weirdness. Right? Yeah. So, number 1 is a homework exercise for you. I'm going to do number 2 because I thought that number 2 was the harder one because it reverses directions, and it might. I think maybe if we can conquer this, it might help you conquer the first one. So let's at least get rolling on this. We're going to start off by saying, let me kind of give a reminder here about how this works. Through to now let me kind of try to recapture, and this will also demonstrate, I think, I want to demonstrate why we've got this kind of reversal going on here. We have home R CD and home R DB to home R 80. Now let's see if we can kind of figure out how this works, right? This is supposed to be induced by G, and this is supposed to be induced by F. So my input, let's just call this, now remember, this is a homomorphism from C to D. So and I need to get a homomorphism from B to D. And so I guess what I need to do is, and of course, G is the one that goes from B to C. So I need to start with G and then this. Everybody agree? On the other hand, when I start with a, let's say, gamma that goes from B to D, gamma needs to go to F of gamma, which is gamma F. Right, because in a certain sense, because of the fact that you're going to D, this forces your reversal of the functions, right? Because to get a function that goes from C to D, and these are the tools you've got, how are you going to go from B to D? You need to do the B function, the one that gets you from B to C first, right? And that's why the order is reversed. Everybody okay so far? I think it's probably safe to leave this as an exercise that these are all homomorphisms. If you struggle with that, please let me know. What we want to do now is, under this assumption, we need to show that this is exact. So the first thing I'm going to do is I want to show that B bar is 1, 1. Right, that's kind of weird, right? Somehow the onto-ness of G is going to give me the one-to-one-ness of this, right? Well, so how's that going to work out for us? Well, I don't know, this guy, tornado, be and the kernel of G bar. This means that G bar of tornado, which is tornado G, is the zero homomorph. This composition is zero homomorphs. Right? Now, of course, what I want to do is I want to show that little tornado guy is actually also the zero homomorphism, right? So here's tornado go, goes from C to D. That's what we need to show. Everybody agree with that? Okay, well, to this end, let's see B and C. Then there exists a B in B such that G of B is equal to C. Everybody agree with that? So notice that now note that tornado G of C sorry, tornado G of B is equal to 0 because tornado G is a 0 now, right? Therefore, equals 0 for all C and C. Because the ontoness lets you cover every possible input there. Therefore, G bar is 1. Everybody okay? We will pick up on this next time. Any questions for right now? Let me plug the math club. Grant Moles is talking today, and he's going to be talking about factorization and lack thereof, and how that connects to some interesting stuff, including Fermat's theorem. Grant's a good speaker. Should be fun. So hopefully I'll see you there for some math pizza. Otherwise, you guys have a good weekend.